Physics 2211 Projectile Motion. The main purpose of this lab is to analyze and compare an object that is moving in a projectile motion to the results of a computational model. In this lab, our object or system is a paper ball, our observed model is determined by tracker, and our predicted model is coded in GlowScript. In a preview of our final result, we found that the predicted model that included drag force was more accurate. So some key concepts that we'll discuss include gravity, drag force, and Newton's second law. Gravity is the attractive force that pulls objects towards the center of the earth. It's what causes objects to fall. Drag force is a resistive force that acts on an object moving through a fluid like air or water and always opposes the motion. And Newton's second law states that an object's acceleration is directly proportional to the net force acting on it, and inversely proportional to its mass. This helps us calculate how the ball accelerates under gravity and drag. For this lab, we made a few assumptions. The only forces acting on the paper ball are gravity and drag, and all standard projectile motion concepts apply. Newton's second law tells us that the net force on an object equals its mass times acceleration, which we can use to calculate motion. The position update shows us the position at each step. Velocity update shows us the velocity at each step by taking into account the net force. The drag force is proportional to the square of the velocity and always points opposite to the direction of the motion. The force of gravity is the mass of the object times the acceleration due to gravity acting downward. So how did we go about this experiment? First, we recorded the video of a paper ball thrown with a constant horizontal velocity. We then imported the video into the tracker program and used the track feature to track individual points of the motion. We created a computational model for predicting the position with and without the drag force and got data. We then created a spreadsheet on Excel to compare tracker data with the data from both computational models and compared the chart of both the computational models and made final conclusions. Our system was a paper ball and our surroundings were forces acting on it like gravity and drag. So the image shows us the setup for tracker in the second step of the procedure. After the video was uploaded, the calibration was set and the axis was modified. Tracker outputted a vertical position versus time graph, which we can use to find the initial velocity by using the first 2 points as shown in the formula. It also gives us the initial position and change in time. So the screenshots above showed the computational model that solely took gravity into account. The mass of the ball was calculated and recorded as 0.0035 kilograms. The initial conditions for position and velocity found by tracker were inputted, and delta t was used as 0.0333 seconds because the video was in 30 fps or 1 frame per 0.0333 seconds. The net force only took gravity into account as shown in the computational model, and the total clip time was 0.532 seconds. So what does it give us? It shows us the position versus time graphs without drag. As you can see, the velocity in the x direction was constant and increasing negatively in the y direction. For the computational model with drag, Fnet was changed to include drag force 2, as seen in the equation, where we added the negative bv squared times normal v. The drag coefficient b was also estimated as 0.003, and we can see that the drag force is resistive. What does this give us? The computational model graphs for position versus time showed that drag had an effect on position in the x and y graphs as they are less uniform. Shown here is the y versus x position graph for tracker data versus only gravity versus including gravity and drag. This graph tells us that including drag in our computational model produces a more accurate result to the real life values. However, there's still some discrepancies between the real life values and just the drag plus gravity, as there are many sources of error that can affect the data. First, human error in tracking the motion of the paper ball could cause small inaccuracies in position or velocity measurements. Our computational model also makes assumptions like ignoring wind and only including drag and gravity, which may not perfectly match real-world conditions. And finally, measurement errors with the calibration stick or timing could also influence the results. So let's go through our discussion questions. Do any of your models predict terminal velocity? No, because none of the models reached maximum falling speed. You will need to drop a light object with a large surface area from a height to find terminal velocity and see when the velocity stops increasing. What if the object was thrown straight up with the same initial speed? Well, the time would be longer since our experiment throws the ball at an angle theta. The original flight time would be t equals 2v initial sine theta over g. When you throw an object straight up, the total time is t equals 2v0 over g. Since sine theta is always less than 1, the original flight time will always be shorter. So what's our conclusions? The gravity model is simpler in code but does not take account for real-world applications like drag. The gravity plus drag model better matches with experimental data.